So welcome back everyone to Mr. Hunter's GCSE physics lessons. Today we're going to look at some more electricity revision. This time we're going to look at some of the key equations and looking at what they do. We're going to have a little look at the resistance in a wire practical, and also some of the IV characteristic graphs that you need to remember what they look like. So let's jump in with the equations that we need. The first important equation is Ohm's law, which is V equals IR. Voltage in volts, current in amps, and resistance in ohms. Now, this lesson and this revision could be used in conjunction with my previous lesson with the truck model, and it builds upon ideas that were covered there. So go look at the truck model to get a foundation into what voltage and current are in the terms of our electricity model that we're using, and then maybe come back to look at these equations. So Ohm's law is very, very important, and most of the problems will stem back to using Ohm's law. We know that electrical power, is P equals IV, where I is current, V is volts from the above equation, and this is power in watts. Now we can sort of analyze this a little bit further if we just change color and look at some units. The amp is the unit of current, and current can be broken down into coulombs per second. And the volt is the joule per coulomb. And those of you who can see through these units, and some of you might be maths whizzes, these two will cancel out, one top, one bottom, leaves us with joules per second. And those physicists among you will realize a joule per second is the same as power, because P, power, is energy per unit time. So all we've done there is we've derived the equation for electrical power. Let's also look at the QUIT formula, or the Q equals IT formula. I'm going to put what should we call it? We'll call it the current charge formula. Doesn't really have a fancy name. Current charge formula. And this just stems from the fact that current is our number of coulomb trucks per second. It's the charge flowing, the flow of charge, or the flow of electrical charge. And so that gives us Q equals IT. We've seen I before. I is current, T is time in seconds, and Q is charge in coulombs. Okay, so that basically sums up all the equations that we need for now. So what I'm going to do is I'm going to plot a little graph, and this is a required practical. This is the resistance in a wire practical. Just color that in, make it look somewhat pretty, although it's not that pretty. Let's draw a circuit. Let's have a battery, whatever charge, whatever voltage it is. Let's draw this out. So I'm going to have here, oh, that's not good. Here we are. And then I'm going to have my voltmeter like this. So I've got current being measured in series, of course, voltage being measured in parallel, and in the middle here I'm going to draw in a ruler with a wire on it. And let's just label this wire. Here's my ruler. Not very pretty, but you'll get the point. These are my two little connectors here, and so I'm going to put these electrical contacts onto my wire. Electrical contacts to complete the circuit. And the investigation was that as you move, you want to measure the voltage and current as you increase the amount of wire that the electricity has to pass through. And so let's just have a little side note. And so you measure amp and voltage as you increase wire length. And so you're increasing the amount of wire that the circuit has to travel through, the current has to travel through in order to complete the circuit. And once you do this experiment, you should end up with a graph that looks like this. This is resistance in ohms, and then this is length of wire in meters. And we should find that this is directly proportional. What is directly proportional? Well, it's a straight line. Oops, can't spell. Straight line passes through the origin. What is our origin? The origin is 0, 0 here, the point 0, 0. Okay, so this leads us into being directly proportional. And if you were doing this experiment, how would you get how would you get R? You would get it from your measurements of amp and voltage. This is currents and voltage via Ohm's law. R is V divided by I. And so you would have a separate column in your experiment to find that out. And so the last thing I want to cover in this lesson are IV characteristics. I'm going to do that again. So something is said to be an ohmic conductor that have a straight line IV characteristic graph. So if we were to pop, let's make some axes on here. You need to remember how all of these look. So I have current on top, on the Y, voltage on the x-axis, and I'm going to plot some lines. I'm going to have light blue like this. I'm going to have slightly darker blue like this. I'm going to have the deepest blue as the steepest blue. And then we can see that these are ohmic. These are ohmic conductors. Why? Straight line. Well, straight line and through the origin. I'm going to be lazy and I'm just going to put they're directly proportional. And we can also see that the highest that's gone wrong. We can see that this one has the lowest resistance. This one has the highest resistance. And how do you know? Always comes back to V equals IR. R is V over I. Then you're looking at the gradients, aren't you? You're looking at the inverse gradient. So the steepest one will have the lowest resistance, and the shallowest one will have the highest resistance, because R is V over I is the inverse of the gradient of this IV characteristic graph we're looking at. Good, so let's look at the last two characteristic graphs. So that one is for the ohmic conductor, this one here. Let's look at one for the filament lamp. Filament lamps are non-ohmic conductors because the IV graph is not linear. The resistance changes as the lamp is switched on. And this one, let's do it in a different color. Let's make it interesting and go for pink. This one looks like this. There's an S shape, and I've been a bit of an amateur and not labelled my axes. So, what has happened then in this conductor, in this filament lamp? Well, as current increases, as I goes up, temperature goes up because we're having more collisions with the electrons, and thermal energy is being generated by the current flowing through the lamp. By definition, a filament lamp is a little bit of metal that gets really hot to glow. That is what sort of old school bulbs are. Of course, we use more modern, more energy efficient bulbs nowadays. But as the current increases here, as the current goes up, the temperature goes up. When the temperature goes up, all the atoms in the filament jiggle around more, and therefore it's harder for the current to flow. Therefore, the resistance goes up. As the resistance goes up, the graph becomes more and more shallow. So it's getting, as we go down, here is a high gradient. Here is a low gradient. In fact, it's a flat line at the end. And from our ohmic conductor graph, we have high resistance at shallow gradients and low resistance at steep gradients. Therefore, the resistance is increasing, and that's how you remember which way around the S shape is. Good. Okay, last one is the diode. And the diode has an activation voltage in which they only let current flow one way. So the graph will look like, let's make it a bit thicker so it's easy to see. The graph will look like this, along here and then up. And why does it look like this? Well, it has a characteristic activation voltage. No current on for negative voltages. No I for negative voltages, as in, and that means only lets current I flow one way, and then afterwards it's linear. I'll put after activation voltage linear. Okay, so that concludes this part of the electricity revision. We have done the diode, the filament lamp, the ohmic conductor IV characteristics. We've done the required practical for resistance in a wire. We looked at the QUIT formula, we derived the formula for electrical power, one which you can do yourself, and we looked at Ohm's law. So that wraps up this part of electricity revision. I hope it's been helpful, and I will see you next time.